Chapter 22, Electromagnetic Waves. So again, this is a chapter summary for Giambattista, College Physics, 5th edition. And it's just a summary, and I'm on chapter 22. So there's a bunch of stuff in this chapter, okay? And it kind of covers it very superficially because you have to. I mean, this is an algebra-based course. Let's just get into it. You know, I have talked about this before, but it's kind of a big idea. Maxwell's equations. And, you know, the book will talk about Maxwell's equations and use them, but I don't really think it's an algebra level course, but we can talk about it conceptually. So let's talk about this conceptually. And I'm going to list these 4 laws. So the first one is Gauss's law. And I always can't remember if that's apostrophe S or just Gauss law or whatever. And I'm not going to even write the equation because it depends on either integrals or vector operations that are weird that you don't want to do. But I'll tell you what this means. Gauss's law is this. That's Gauss's law. And that's the electric field. So Gauss's law says that charges make electric fields. And the shape of these fields depends on the distribution of the charges. If you have a point charge, that a positive point charge, that electric field points away. That's what that says. And then we have another one. I'll write it over here. This is Gauss's law. I see I left off the S. Law. And I'm going to put 4B. Gauss's law for magnetism. And it looks like this. That's it. It's just like this. But there are no magnetic charges. We have never seen a magnetic charge. So you can't make a magnetic field B that looks like this. Right? That looks like the electric field. You can't do that. That's what Gauss's law for magnetism says. Okay. Now, I'm trying to decide how to draw this. We have Faraday's law. This says, let me write this like this. This is the magnetic field coming out of the page. Remember, if you draw circles like that. And this would be, oh, that was a bad one. E, B. And this is changing, oh gosh, that was so bad. Changing B. So this says that a changing magnetic field, that has to be changing, you can't even draw the changing because it's paper doesn't change. A changing magnetic field creates an electric field. And the shape of that electric field, I'll call this curly E. Just to say the difference, right? Because this electric field is completely different than that one. That one points away from positive charges. This is like making circles. So a changing magnetic field makes curly electric field. And then finally we have the Ampere Maxwell law. And I'm going to draw it like this. This is the electric field. That's an E. And these are all coming out of the paper. One more. And then I can have changing. If it's changing, oh, I shouldn't even put that arrow there. So this says a changing electric field makes a curly magnetic field. Or a current. Let's see, wait, that's backwards. I'll fix this. So there's 2 ways to make a curly magnetic field. I can have a moving charges, an electric current, or I could have a changing electric field. There's 2 ways to make electric field. One of them makes a curly electric field, changing magnetic field, and electric charges make just normal electric fields. That's Gauss's law. Okay, the math of it is not trivial, but it's super important. These 2, you can see, are super important because this says if I have a changing magnetic field, that makes an electric field. If I have a changing electric field, that makes a magnetic field. So these 2 things work together. We don't even need the charges. We can make a changing electric field that makes a changing magnetic field. A changing magnetic field makes a changing electric field. And that is an electromagnetic wave. And it turns out that, and that you can do this wave equation and all that stuff, but it does involve quite a bit of stuff. So you can use Maxwell's equations and show that it does indeed make a wave. It's kind of a big deal. It's a big deal because if I have a wave, and I'm going to draw a wave right here, a repeating wave of electric fields. This is the electric field. I'll just draw one. That's the electric field. We're going to have, if it's the wave is moving this way at some velocity, with some velocity direction v, then the magnetic field is going to be this way and perpendicular to that. And that's an electromagnetic wave. That's kind of a good picture. It's kind of a big deal because since this wave has two parts that work on each other, it doesn't need a medium. You can travel through empty space, which is, sound doesn't travel through empty space. Other waves don't. You can't have a wave on a string if you don't have a string, but you can have an electromagnetic wave if there's nothing there, and that's kind of a big deal. We can calculate the speed of this wave using Maxwell's equations, and we get 1 over the square root of mu naught epsilon naught, and we call that c, the speed of light, which is 3 times 10 to the 8th meters per second. And if you remember, that was the epsilon naught from Coulomb's law. This is the mu naught from the magnetic force and the magnetic field. So that's the magnetic constant, the electric constant. They're just numbers, but if you do put them in there, you get the speed of light. Now, the other thing is, if you measure the wavelength of a wave and compare that to the frequency, this is true for all waves, then for any waves, we can say the speed is the wavelength times the frequency. Okay, so if the wavelength's in meters, the frequency's in hertz, meters times hertz, which is 1 over seconds, gives you meters per second. Okay, and I put a v there because sometimes the light does go at different speeds than v, and I just want to put that in there. The next thing that we have is this idea of, they talk about dipole antennas and loop antennas, and the physics of that is the important thing to know is, how do you make an electromagnetic wave? Well, you have to have a changing electric field, and one way you could do that is to have an accelerated charge. So you have a charge, let's say like this, that oscillates back and forth, and it'll be accelerating, and that will create an electromagnetic wave. So accelerated charges make electromagnetic waves. If you have a radio antenna like this, you can send current up and down the antenna, and it will make an electromagnetic wave. That's a radio station, or a cell tower, or your phone, because your phone sends out radio waves. Okay, next, electromagnetic spectrum. I'm going to say EM spectrum. So it turns out that different wavelengths of electromagnetic waves interact differently with matter. So we break them up into different classes just for fun. And so the lowest will go from large frequency, large lambda, which would be low frequency, to to small. I don't know why I'm confusing those. Then we'll start with radio waves. And these can be very large wavelengths. We don't have there's only one of them that really have a finite range on. So radio waves can be, meters long, centimeters long, and so forth. And when you get a little bit smaller, you get into the microwave range. Yes, that's what your microwave uses. It shoots electromagnetic waves of the microwave wavelength, and it turns out that a particular frequency, a particular wavelength, interacts really well with water and can make it oscillate, and that's what a microwave does. It turns out that a lot of our telecommunications, I think LTE for your phone is in the microwave region, Wi-Fi is in the microwave region, and that's why when you turn on the microwave, sometimes it messes up your Wi-Fi at your house. Okay, the next we have infrared. I'm a huge infrared fan. I have infrared cameras. I love infrared cameras. It turns out that when you have an object that has temperature, which is everything, it produces electromagnetic radiation. And for most objects that we deal with, that wavelength falls in the infrared region. So everything around you is producing light. You just can't see it with your eyes because your eyes don't detect that. And as you get smaller and smaller wavelengths, we get what's called the near infrared. That's what your TV remote uses, but it's still all infrared. And then we have the visible spectrum. And this is the one I'm going to give a list from. This is from red light of 700 nanometer wavelength to violet light of about 400 nanometers. And so this is where you get the, I'll put it over here, red, orange, yellow, green, blue, indigo, violet. That's the spectrum of colors of visible light. And you'll notice this is a really small spectrum, right? It only goes 300 nanometers wide. It's a super tiny thing, but this is the range that our eyes detect, and we call that the visible spectrum. There's a whole bunch of fun things to talk about, but we'll save that for another day because we're just doing a summary here. And then we have, and you'll notice infrared is right below in terms of frequency, visible light. And then we have ultraviolet, I'll just call it UV, that's just above. And then we have, I guess we'd go into, am I skipping one? X-rays and gamma rays. So, X-rays, gamma rays, I think they came from a time from before everyone knew exactly what was going on, and they called them rays, because there's also like beta rays, which are electrons, and they're not X-rays, and there's, so that's just a thing, just so you know. Yeah. So that's your wavelength. Gamma rays, the Hulk. I had to say that, the Hulk. Okay, let's move on. What is next? I talked about this. This is an important thing. The direction of a wave that it travels, it's such that the velocity v is in the direction, the direction of v, not the value, is in the direction of E cross B. So this is the right-hand rule, right? We did this before with QV cross B as the force. Same thing. It's the same right-hand rule from the electric field. So you cross electric into magnetic field, and then your product shows you the direction of the velocity. And that's just unit vectors. They're not actually, the units don't work there. This is an important one. The magnitude of the electric field is equal to C times the magnitude of the magnetic field. So they are related. You can't have just any value for electric. If you know the value of the electric field and it changes with time, right, it goes up and down, then you know the magnetic field, and they're in phase. So when this is the greatest, that's the greatest. When that's zero, that's zero. Now, we can use this. I don't remember where it did it. I'll put it over here. We do have this index of refraction. And this is going to be really important later. I'll just put ref. And it's N is C over V. So this is the ratio of the speed of light in a vacuum to the speed of light in a material. So if you shine light into glass, the light travels slower. And so if you divide C by a smaller number, you get an index of refraction greater than 1. So the greater this number, the greater the index of refraction. And it matters because then we're dealing with things, when we change the speed of a wave, you can get some effects. One is you get bending of the wave, and that's refraction, and we'll talk about that in optics. But that's the index of refraction. It has no units because we're speed over speed. Back to this. So let's talk about the energy density in an electromagnetic wave. So remember that the energy density in the electric field is 1/2 epsilon naught the magnitude of the electric field squared, and the energy density in the magnetic field is 1/2 1 over mu naught b squared. So if this is true, this relationship is true, then it turns out in a wave, the energy density of the electric field and magnetic field is the same. So let's show that right here. So if this is true, then the magnitude of b squared is going to be E squared over C. But remember that C is 1 over the square root of mu naught epsilon naught. No, this is squared. That's right. I have to square both of those. So this is going to be squared. So it's going to be 1 over mu naught epsilon naught is C. Now if I put that in over here for B squared, I get UB, the energy density for the magnetic field, 1/2 1 over mu naught. Now I'm going to put in E squared, and then 1 over C squared is this. So it's mu naught epsilon naught. So I get 1/2 epsilon naught E squared, right? Because the mu naughts cancel. And that is the same as this. So that means that the total energy density in an EM wave is going to be equal to UE plus UB. And so they're both 1/2 epsilon naught E. I can write this as just epsilon naught E squared. And that's the not really, that's assumed, we assumed this was a constant electric field. So it's not. So maybe we should write this as the average U, if we average it over a time, is going to be equal to epsilon naught times the average E squared, which is equal to 1 over mu naught average B squared. And that's the energy density. That's the energy density for an electromagnetic wave. So remember, U is the total energy divided by the volume. Now, one of the things that we're going to look at is power. So remember that power is energy over the change in time. And that leads us to intensity. Intensity. So we define intensity of light as the average power per area. So if you imagine a light bulb right here, and it radiates light, that light has energy, and it moves with time, so there's power. But if I want to encircle the whole thing, then I could capture the power of this light bulb. Let's say it's a 10-watt bulb, and this would be the area of the whole thing. Then you'll notice that as you get further away from the bulb, the area that it's spread over is larger, and so the intensity is less. This is kind of a big deal. This would be in watts per square meter, because we use this a lot in things like astronomy or any situation where you have light expanding and it doesn't appear as bright. So this is how bright it appears, right? The intensity, which is with the same thing we use anyway. Okay, let's write this out, the intensity, in terms of the energy field density, the electric field density, or the light energy density. So I can, if the power is the energy per time, then I can actually write this as the energy. So let's write this as I as the average energy, and I'm going to call that En for energy, over time. But then I have the area down there too, over delta T. That's the same thing, right? Now I can write the average energy density as the energy density times the volume. So this is going to be U, the average energy density, times VOL, A, delta T. Don't confuse that with velocity or voltage. It's the volume. And so this is the energy, and this divided by that is the power. Now imagine that I have a block of light like this, and it's traveling this way. And so let's call this the distance S, and we'll call that A. So the volume is going to be S over A, S times A. So I get USA, look at that, divided by A delta T. Those cancel. S over delta T, since this is light, that's the speed, S over delta T. So I actually get this. That's the intensity of light. It depends on the energy density, which can change, right? Because as you get further away, the energy density decreases, and that's the speed of light. Okay. And since this depends on the electric field, we can actually say the intensity is proportional to the square of the electric field, which is proportional to the square of the magnetic field. Okay. Two more things. One, I don't want to talk about this too much. Polarization. Imagine you were looking at electromagnetic waves and you were just concerned with the electric field, and it's coming out of the paper. It may have an oscillation up and down like that, but it also may oscillate this way, or that way, which I've already done, or that way. And so we call this no preferred direction for oscillation, and we call that unpolarized light. It's possible to take this and pass it through a filter, and we're left with only oscillations in the same direction. We force them only to go up and down or whatever we want, and that would be polarized. This is actually called linearly polarized, but so if you take unpolarized light and you pass it through a filter, and this has an intensity of I0, this would have an intensity of I0 over 2, because you're essentially cutting out half the light. And this, if this is polar in that orientation it passes through, it doesn't go away, it just gets reduced. Now, if I take polarized light and pass it through another polarizer with some angle theta, and it's kind of hard to draw this way because I'm going this way. I'm actually coming out of the paper. Then the intensity over here is going to be I0 times cosine squared of theta, where theta is the angle between the oscillation vector and it's the angle, the orientation angle between these two polarizers. That's that. I forgot there was I did up here. Let me go back up here. It's this power. I forgot a power thing. If you have light shining on a surface, this is actually important. Here's some area A. Then the intensity, the power that the light gets, the average power is IA cosine theta. And so this, if you draw a line normal to that area, this angle right here is theta, the angle between the light and the line normal to that. So if you want to increase the power for a solar panel, this comes up with solar panels, you want this normal line to be in the same direction as the light so that theta is 0. Okay, I said it. Okay, one more thing. This is the Doppler effect. And this is the same Doppler effect that we have for sound. When an object is moving towards you very fast and you listen to it, it sounds at a higher pitch. When it moves away from you, it sounds at a lower pitch. We see that in a lot of different situations all over the place. The same thing happens with light. And so we have this equation. This is the Doppler. I'm not going to derive it. Square root of 1 minus V rel over C over 1. Oh, this is plus. It's minus V rel over C. So this says the observed frequency of light is the frequency at the source times 1 plus the velocity relative to the observer divided by the speed of light divided by 1 minus the velocity relative to the observer divided by the speed of light. And so you'll see if you're moving really slow and C is really large, then you don't get a noticeable thing. You need to be moving close to the speed of light if you wanted to see that. Now, if it's going really slow, we can actually write this as approximately Fs 1 plus V rel over C. And that's the Doppler shift. So it actually really is important for detecting extrasolar planets, measuring the speed of stars moving towards or away from us and all that stuff. You can also use this for radar to detect the speed of cars because you're looking at the frequency shift for light that radar waves, which are, I guess, microwaves, traveling towards the car and bouncing off, and then you get a shift from that, and that's how you can determine the speed. Whew, like I said, I feel like that was more than 23 minutes, but that's chapter 22. It's a lot of stuff. They have some other good examples in there. I didn't go over all the examples. I think the most important thing is this idea of what is an electromagnetic wave, frequency, wavelength, speed, intensity. Those are my biggest things in the chapter. I like energy density too, but really that's it for me.